In the continuation of my lecture 7, mechanical work, today I shall complete this part of this chapter. And already I have said for this is the expressions of this mechanical work or the work associated with the pressure volume. And these expressions of this mechanical work is the minus integration V1 to V2 and P external dV. P external is the pressure exerted by the surroundings on the piston, and dV the volume change, and in this case this volume change occurs from V1 to V2. This is the IUPAC convention. And whenever the reversible process occurs, say for reversible compression, then P external equal to P internal plus dP, and dP tends to 0. So in that case, the external pressure is equal to the pressure of this internal pressure, or means the pressure of this gas. In this case also, in the case of expansion, this P external equal to P internal minus dP, and the gas expansion. It is to be remembered, I have already told the external pressure that we can control, but internal pressure it is the pressure of this gas. It is beyond our control. So now, if we consider the reversible cyclic process, what will be the amount of mechanical work involved in case of reversible cyclic process? We can draw a picture, and this is the external pressure. P external means pressure exerted by this piston, or by putting this weight over this the piston, and it is V1. Here, suppose, let us consider the 1 mole ideal gas, and the process is isothermal. For the sake of simplicity, we can take it, the process is isothermal, reversible, involving 1 mole gas, 1 mole ideal gas, 1 mole ideal gas. So it is V2. This is the W1 compression, means work done on the system, and comes to this V2, and whenever it goes to V2 to V1, this cycle is complete. Means the whole process is consisting of the one compression and one expansion. In this case, this is suppose work involved is W2. So this according to the formula that I have already derived, this W1 equal to this RT ln V2 by V1, and here it is minus. This is the amount required for this system to compress from V1 to V2. And again W2, whenever it is again coming to this initial state by
by expansion, it is minus RT, T is constant, this process is isothermal, and ln V1 by V2. Or we can write RT and ln V2 by V1. So what we are saying, the magnitude of these two works will be the same, only the reversing sign, and the total work W equal to this W1 plus W2, and this sum of these two becomes equal to 0. What does it mean? Means the net work in this reversible cyclic process is equal to 0. For the cyclic process, W cycle equal to 0. This is why it is called the irreversible process. Means the system can be brought back to its initial state without the requirement of this external agency or external work. And this is a very ideal process, and the system, whenever this is isothermal process, one thing I can say, the walls are dithermal wall, means fully heat conducting, and the system and surrounding heat is freely exchanged to keep this temperature fixed. Or we can do it in a thermostat of this fixed temperature. Next, I come to this irreversible process. What will be the magnitude of work, mechanical work, in this irreversible process? And you all know all the natural processes are irreversible processes, and a reversible process is in case of irreversible process, no restriction has been applied for undergoing the successive stages of infinitesimal amount of change of pressure or of volume. This is either one step, and this is a real process. And the irreversible process, the mechanical work done equal to irreversible process, in case of mechanical work done, equal to, suppose this is the figure, here it is P1 and it is P1, and the compression occurs here V2 and the P1 to P2. Here suppose N moles ideal gas have been taken, and while I am dealing with this irreversible process, always I shall take this ideal gas as the equation for this ideal gas is very much handy, and mathematics is also very same to do. And so the work done, mechanical work done in this process is the minus P2 into V2 minus V1, and P2 is the external pressure, final external pressure. Suddenly this change is occurring at a constant external pressure of P2, means the gas is compressed. The gas is compressed against constant external pressure. External pressure P2, and it is the volume change. This is final volume and this is the initial volume. And this irreversible process we can do also in two ways: isothermal irreversible process and adiabatic irreversible process. Let us formulate the magnitude of this work for these two type of processes. And A, it is isothermal irreversible process. Here T is kept fixed. So naturally what I told, this is the system and this is surrounding, and system and surrounding heat exchange is continued. As you know, whenever there occurs an expansion, there will be fall in temperature. So keep this temperature fixed at a certain value. The heat must enter from this surrounding to the system in case of the expansion, or in case of compression, heat will be going out from the system to the surrounding in order to keep this temperature fixed. And the walls are completely heat conducting or dithermal. So in this case, work done in irreversible and isothermal, and this one equal to minus P2, and in case of V2 equal to nRT divided by P2, and V1 equal to nRT. T is constant and T1. Naturally, we are using this ideal gas in this system, and V is replaced in terms of this pressure. So nRT divided by P2 and minus nRT divided by P1. Bracket close. So if we bring this N out, nRT outside of this bracket, and P2 is keeping inside this bracket, then it will be 1 minus P2 by P1. So this one thing is that the expression of irreversible and isothermal equal to minus nRT and 1 minus P2 by P1. This is irreversible, ideal gas, irreversible, and isothermal. Process. One thing I like to mention here, that we always try to express the magnitude of any term in terms of this intensive properties. Here, instead of volume, I replace here the temperature and pressure. As the temperature and pressure, these are the intensive properties which are usually used to express the magnitude of this of any property. So if we consider this second one, adiabatic irreversible process, then naturally these walls are no longer dithermal, walls are wrapped by good insulator so that the heat cannot exchange between the system and surrounding. And this is the adiabatic walls. This is the adiabatic walls. Piston is also adiabatic walls. And adiabatic irreversible process, we can use this first law. First law, Q plus W equal to du. But for the adiabatic process, Q equal to 0, as the walls are wrapped by this good insulator, heat cannot be exchanged between the system and surrounding. So this will be W equal to dE. Naturally, whenever this work, very simple, whenever the work is done on the system, means energy is flowing from the surrounding to the system, and the system's internal energy will increase. But whenever the system does some work, means work done by the system, then heat is flowing from the system to surrounding, and the system will lose this internal energy. Internal energy is decreased, means in that case work is done by the system at the cost of its own internal energy. For n moles ideal gas, this dU equal to NCV T2 dash minus T1. Let the temperature, final temperature for this adiabatic irreversible process is T2 dash. Here T2 dash is the final temperature in the irreversible adiabatic process. It can be shown very easily that if the process would be conducted in adiabatic reversible process, then the final temperature will be much less than T2 dash. And T2 dash could not be calculated by the use this P1 gamma and T1 1 minus gamma equal to these usual rules, T1 to the power gamma and P1 to the power 1 minus gamma equal to T2 and T2 gamma and P2 to the power 1 minus gamma. This relation cannot be used in case of irreversible adiabatic process. This relation is valid only when the process is reversible, adiabatic and the ideal gas. So, this W irreversible adiabatic, this one equal to N PV, N CV and T2 dash minus T1. If we can determine this T2 dash, then this magnitude of this work for this irreversible adiabatic process could be done. Now let me see how this T2 dash could be calculated by using this first law of thermodynamics for this ideal gas. This relation is not valid. So So let us see how this T2 dash could be calculated. Again, I can remember the first law for adiabatic process. For adiabatic process, this W equal to du. And this for this irreversible process, this W will be equal to minus P2 into V2 minus V1. And P2 is the final pressure against which this compression is made, and this one equal to mCV. Instead of du, I can write mCV T2 dash minus T1. So again, like V2 minus P2 into, instead of V2, I can write N or T2 dash divided by V2. As you know, for this adiabatic process, there must be the change in temperature. If this adiabatic expansion, then temperature falls. If the adiabatic compression, then temperature of this gas will rise. So this one minus Nr T1 divided by V1 using this ideal gas laws equal to NCV and T2 dash minus T1. T1 is the initial temperature. P1 is the initial pressure, P1 is the initial pressure, P2 is the final pressure, and so this minus Nr, you can take this common, and P2 here T2 dash P2 1 and minus T1 into P2 by P1, and this is equal to NCV T2 dash minus T1. And N cancels, so we can find out the value of this T2 dash from this relation. Or better, I can also transfer this minus nRT2 here, then then R T2 dash minus goes here plus, and plus CV T2 dash equal to here also T1 R T1, this is coming here, so this is coming here, so minus plus CV T1, and here minus plus R T1 and P2 by P1, and bracket close. Or I can take this common T2 dash, and here R plus CV equal to, here T1 gets common, and CV plus R into P2 by P1. T1 gets a common, CV plus R P2 by, or R plus CV. For ideal gas, R equal to Cp minus Cv plus Cv, it is equal to Cp. So T2 dash equal to T1 by Cp, and here Cv plus R and P2 by P1. So this is the expression how this T2, the final temperature for irreversible adiabatic process, could be calculated from this initial T1 temperature and P1 pressure and final pressure P2. Here also this temperature is expressed in terms of this intensive properties. And whenever this T2 is put here, then we shall get this amount of mechanical work involved in this irreversible adiabatic process. Now I shall find out what will be the amount of work in irreversible cyclic process. This is very important. Irreversible cyclic process. Irreversible cyclic process. Let us consider very simple case. This 1 mole ideal gas undergoes adiabatic, undergoes the isothermal irreversible process in 2 steps only. In 2 steps only. Here it is, say this is first step and work is W1, and in case of the cyclic process this is also goes here and this is a W2. And this field for this adiabatic process, this one is the work done as the compression work done on the system, and this is the amount of work done by the system to bring it back to its initial state. So this W1 equal to minus this compression occurs against the pressure P2, and then P2 into V2 minus V1. And similarly the W2 equal to, in case of expansion, what occurs against the external pressure P1 minus P1 into V2 into V1 minus V2. V1 is the final state, final volume, V2 is the initial volume. So this one we can write this P1 and V2 minus V1. So the amount of work in irreversible cyclic process equal to this W1 plus W2, and this one equal to P1 minus P2, adding this 2, and V2 minus V1. And suppose for any process, say for compression, say W1 is the compression, this is the compression, and this is expansion. And by these 2 steps, the system comes back to its initial state. And here, this P1 is less than P2, and P1 is greater than P2.
So this P2 is greater, means this term is negative, and V1, V2 is less, V1 is greater, so this term is also negative. So both sub product of these two terms is negative into negative, so this one is the positive. What does it mean? It is very peculiar to say this W in cycle for this irreversible cyclic process, this one not equal to 0 and this one is positive. What does it mean? Means amount of work is required for this irreversible process to bring back the system to its initial state. This is why it is called irreversible, means not reversible. The initial state could not be could not be reversed without the aid of external agency. Some amount of work is to be added. This is to bring the system back to its initial state. This is a very simple case. And in case of magnitude, we can say this W1 is positive. W1 in this case, W1 is positive, this one is negative. So W1 more amount of work is required to compress than the work we receive in this expansion. So this one is greater than W2. Means more work is required to compress, but this work received, what is done by this system is less in comparison in this irreversible process. Very interesting example I can set here. Suppose we are considering the hydroelectric project in Ajodhya, and in case of Ajodhya, which has been established in or completed in 2008 in collaboration with this Japan. Say suppose this is the hill in Ajodhya at Purulia district. Here is a dam, and this is called upper dam. And here also another dam. This is lower dam. These are the heat reserve. These are the water reservoirs. And here, from this lower dam, and it is also lower dam, here the water is lifted to this upper dam by means of electrical pump. Here is the electrical pump. By this electrical pump, water pump, this water is lifted from this lower dam to this upper dam, and here the water is stored. And this is W1. Water is lifted, energy is required, and the electrical energy is required to lift this water from this lower dam to this upper dam. And again, this one and here now this water is flowing
from this upper dam to this lower dam. And here if we put one generator, electrical generator, it will produce this electricity, and this electrical energy is so received by this generator is the W2. And from the initial state, the water again comes to its lower dam, and repeatedly this water is again lifted and again comes to this lower dam. This is W1, this is W2. Here water, here work is required, here work we shall get it. So electrical work you can say. So in the, like this one, this W1 will be always greater than W2. Means the system, if we like to bring back, or if we like to water to bring to this lower dam again, then more work has to be spent on. And now I try to explain the comparison between reverse work done in a reversible process and work done in this irreversible process, which is the greater one. And here also one more ideal gas has been taken in isothermal let us make a comparison between the work done in reversible process and work done in irreversible process. And I have already defined what are the difference between this reversible process and irreversible process. In case of irreversible process, the volume change occurs against a constant external pressure. But in case of reversible process, it is a multi-step process. In every step, the system attains equilibrium. So let us take let us take a simple case, 1 mole ideal gas in isothermal process. So this is the system, and it is the V1 and coming to V2 compressed, and it is the P1 and giving to at this P2, and this system comes to this one. Here 1 mole ideal gas. So it is a case of compression. It is a case of compression of this 1 mole ideal gas in this irreversible and reversible processes. And W reversible for this isothermal process, RT ln P1 by P2. Already I have formulated this sort of equations. This could be written as RT and ln, and here 1 plus and this P1 minus P2 and divided by P2. So if a P1 minus P2 divided by P2 is not very large, then it could be written as RV equal to, and it is isothermal process, RT, and here P1 minus P2 divided by P2. As ln 1 plus x almost equal to x when x is much smaller than 1.
X is much smaller, much small in comparison to 1. So again, this work done in, we can show if it is compression, then P1 is less, P2 is greater, and this one is negative, and here minus. If we consider the compression, P2 is greater than P1, so this one is negative, negative and a negative becomes a positive, work done is positive. So for work done in irreversible process, this could be written as, for this isothermal, minus RT and 1 minus P2 by P1. So this is equal to RT and P1 minus P2 and divided by P1, and here it is minus. So if we consider the magnitude, then this one is the greater and this one is the less, as P2 is P2, if we consider P2 is, and this is the expressions. Now further we shall case what will be the which one will be greater in case of the reversible process, in case of compression, and in case of expansion. So this W reversible minus W irreversible, difference of these two, we shall see this one minus RT and P1 minus P2 divided by P2 and minus plus RT ln P1 minus P2 divided by P1. All this difference is RT gets common and minus, so and P1 minus P2 also gets common, so it will be 1 by P1 minus 1 by P2. It is P2 minus taken common, and it is P1. Or we can write minus RT, and when this subtraction is done, then P1 minus P2 whole square and divided by P1 P2. And since it is the square term, P1 or P2, which may be greater, we need not know. This square term is always positive, and these are positives, RT positives, so this one is negative. What does it mean? In case of compression, this work done in reversible process is less than work done in reversible process. Means if we do this compression in reversible process, then more work has to be spent. More work is to be spent. For irreversible compression of this gas. But if we do this expansion process, then this one we can show this work reversible minus work irreversible, this one becomes a positive. So negative sign will be developed. And in that case, this one is greater than this one. So whenever this expansion occurs, the system will do more work. In reversible process, than in irreversible process, and this is why we always choose the reversible process for getting the more work done by the system. And this could also be shown by means of indicator diagram very easily. Indicator diagram, say this is the volume and this is the pressure, and this is V2 final volume, and this one is V1. And whenever the reversible process is reversible process is done in isothermal way, reversible and isothermal, so it will be the rectangular hyperbola, and this one is the amount of work done in this area equal to the work done in a reversible isothermal process or work done in reversible process. If it is done in irreversible from V1 to V2 compressions, then it is P1 and V1, and this is the P2 and V2. In this case, the amount of work done is P2 into the volume change, so this will be the area. So this will be the area for work done in irreversible process for compression. So this one is the greater and this one is the less. What is required to compress in case of irreversible process? If we do the expansion, I shall also draw, and this one, and this is P, and here it is V1, and here it is V2, and again this is isothermal, and this is isothermal process. This is reversible isothermal, and this one, area under this curve will give you this area, will give you the work done in reversible process, reversible expansion. V1 to V2. V2 is greater than V1. So whenever this was done in irreversible process, this one is the P2 V2, and here it is P1 V1, and this one, the area work done in irreversible process. So in this case, whenever the expansion occurs, then work done in reversible process is always greater than work done in irreversible process. So this is all about this mechanical work in case of the reversible process. Now I like to give some two problems to illustrate the subject matter. Now I illustrate this chapter, this portion, mechanical work, in terms of two problems. Problem number one, which has been placed in IIT KGP. This problem has been set in IIT KGP 2000. The problem is 1 mole steam is compressed reversibly to liquid water at its boiling point 100 degrees centigrade. The heat of evaporation of water at 100 degrees centigrade and 1 atmosphere pressure is 2258 joule gram inverse. And the problem is like this: 1 mole steam converted to 1 mole water, temperature and pressure remaining the same, and so we have to determine, calculate Q, W, del Q, del H of the process. Process is like this. So Q here, the latent heat of condensation, and the latent heat of condensation, so this will be, heat will be liberated, minus 80 watt per mole, and it is given here per gram. So multiplication of this 2 will give you minus 646 joule mole inverse. And the work is minus P into final volume VA minus initial volume Vg. So this is equal to VA is very small in comparison to Vg. So we can write this one a PVg. And PVg, if we assume this steam behaves ideally and follows this equation PV equal to RT, then instead of PV we can write W equal to RT. So putting these values, R equal to 8.31 joule mole inverse Kelvin inverse, and the temperature is 100 degrees centigrade, means 373 Kelvin. So this amount of work done on the system is this one, 3099 joule mole inverse. Whenever we are trying to calculate this delta U according to the first law of thermodynamics, Q plus W. Q is this value and W is this value, and the final result minus 37,547 joule mole inverse. And delta H is nothing but the heat change at constant pressure. Here heat of condensation, so minus this one is the delta H. Now I give one second problem. In case of A and B, both the process are there. One is reversible and reversible adiabatic, and this one is the irreversible adiabatic. 1 mole of a monoatomic gas at 27 degrees centigrade and 1 atmosphere pressure is adiabatically and reversibly compressed to a final pressure of 10 atmospheres. Evaluate the final temperature and also find out W, delta U and delta H. And second one, whenever it is irreversible, evaluate again the final temperature and the values of W, delta U and delta H when the process occurs irreversibly against a constant pressure of 10 atmosphere. And these are the required formula to solve this problem. T2 for this A reversal process, T2 equal to T1 into P2 minus by P1 into gamma minus 1 by gamma for reversible adiabatic ideal gas. And so what reversible adiabatic equal to NCB T2 minus T1, and this one is for irreversible adiabatic ideal gas. T2 dash equal to T1 by Cp into Cp plus R into P2 by P1. And this one, and what in irreversible adiabatic process is the same NCB here T2 dash minus 1. So gamma equal to Cp by Cv equal to 5 by 3 as the gas is monoatomic. So Cp solving again Cp minus Cv equal to R calorie. So if we solve these two equations, so then Cp equal to 5 calorie mole inverse Kelvin inverse, and Cv is also 3 calorie mole inverse Kelvin inverse. So these are the formula required. So whenever I try to solve this problem A, T2 equal to 300 Kelvin, and P2 10 atmosphere, P1 1 atmosphere, and gamma equal to 1.66 minus 1 divided by 1.66, and the value comes up 750 Kelvin. Delta U equal to NCV T2 minus T1, N 1 mole and CV 3 calorie, mole inverse Kelvin inverse, and T2 750 calorie already calculated, and the initial temperature minus initial temperature 300 Kelvin. So this is 1350 calorie. Delta H equal to NCPT2 minus T1. So this is equal to 1 mole 5 calorie mole inverse Kelvin inverse. Cp is 5 calorie mole inverse Kelvin inverse, and 750 minus 300, and this will give you 3250 calorie. Delta H is greater than delta U. And the work first law, Q plus W equal to delta E, but for adiabatic process Q equal to 0. So W equal to delta U and W equal to delta U here, 1350 calorie. And for this solutions to the second problem B, whenever the process is irreversible adiabatic, this T2 dash is to be calculated by this formula, and here T1 300 Kelvin and Cp 5 calorie mole inverse Kelvin inverse, and Cv equal to 3 calorie mole inverse Kelvin inverse here given, plus R, the value of R at 2 calorie mole inverse Kelvin, and this one gives the 1380 calorie. It is to be noted that the temperature, final temperature T2 dash is much greater than this final temperature in reversible process, almost double. In that case it was 750 Kelvin, here 1380 calorie. So delta U equal to NCV T2 dash minus T1 equal to 1 mole 3 calorie mole inverse Kelvin inverse, here 1380 minus 300 Kelvin, and this is 3240 calorie. And the next delta H equal to NCP T2 dash minus T1. So this value also coming to 5400 calorie. And this W similarly Q plus W equal to delta U. So Q equal to 0. So del W equal to the delta U, and delta U this value 3240 calories. This is all about these two problems. It is a good matching to show how the changes are occurring in this reversible process, reversible adiabatic and irreversible adiabatic. So thank you all, and today in this day this lectures on first law of thermodynamics is complete, and next day next class I shall start this thermochemistry, which is the applications of this first law of thermodynamics. So thank you all who are watching my video, and if you like, then please subscribe.